Hello and welcome to day 17 of Advent of Code 2024. So, in this puzzle, the historians push the button on their strange device, but this time you all just feel like you're falling. Situation critical, the device announced in a familiar voice. Bootstrapping process failed. Initializing debugger. So the small handheld device suddenly unfolds into an entire computer. The historians look around nervously before one of them tosses it at you. So this seems to be a 3-bit computer. Its program is a list of 3-bit numbers 0 to 7, like 0, 1, 2, 3. So the computer also has 3 registers named A, B, and C, but these registers aren't limited to just 3 bits and can instead hold any integer. The computer knows 8 instructions, each identified by a 3-bit number called the instruction opcode. And each instruction also reads the 3-bit number after it as an input. This is called an operand. The number called the instruction pointer identifies the position in the program from which the next opcode will be read. It starts at 0, pointed at the first 3-bit number in the program, except for jump instructions. The instruction pointer increases by 2 after each instruction is processed to move past the instruction pointer the instruction's opcode and its operand. If the computer tries to read an opcode past the end of the program, it instead halts. So the program 0, 1, 2, 3 would run the instruction whose opcode is 0 and pass it in its operand of 1, then run the instruction having opcode 2 and pass it the operand 3, then halt. So there are 2 types of operands. Each instruction specifies the type of its operand. The value of a literal operand is the operand itself. For example, the value of the literal operand 7 is the number 7. The value of a combo operand can be found as follows. Combo operands 0 through 3 represent literal values 0 to 3. Combo operand 4 represents the value of register A, 5 in B, 6 in C, and 7 is reserved and will not appear in any valid programs. So this puzzle is a kind of computer simulation, and I think it's the most similar thing would be the int code computer in Advent of Code 2019. So if you did that year, you probably will probably recognize this a bit, but it's a little bit different anyway. So here they are actually explaining all the different opcodes, what they do, and here we see some examples. So what we need to do is to find the output, find out what the output is basically. So we have this example. We set the register A to this value. The other will be 0 at start, and we're giving this program here to run. And after running this example, we will get this output. So that kind of let you think that the output would be some kind of a comma separated integer list. So I will. So my thinking here, just to do this a bit quicker. We will look at these instructions separately. So let's go to the code. So I kind of just prepared it because you could obviously do this. You could obviously read in the input file and parse them, but as the input file input file or the input puzzle data is only 4 lines long, where one of the, well, 5 lines actually, and one of the lines is a blank line. So I find it a bit unnecessary actually. So I only did it like this. So we set the a register or a variable. You can actually think about them as variables to 729. So that was the example here, 729, and the program is that list of integers. So to do this, I will do a function or a method that runs this program. So we will actually have this static, and we will output a list of integers, and it will call run program, and we will take in our list of integers as a program, and we will also take in our, well, no, we will actually do this as a long, because these values can be larger than integers at least for the real data, the real input. So we will have a long a, and yeah, so we kind of, so I'm just going to do this a little bit quicker here, so we have our instruction pointer, we have our B and C registers or variables as well. We're just gonna set the A from before. We will also have our output, which will be a list of integers. No, we can actually do it like this. We will actually have we will output the long instead, and that because it will make the calculations a bit easier. It will not be a long, of course, because the values will never exceed integers. Of course, they will just be smaller numbers, but the calculations we're going to do will it be easier if we actually have longs as well, all the way around. But the program will still be a list of integers because we know it is integers. So yeah, so this method will return the output. Yeah. So we will do a while loop through our program. So the so the instruction pointer will actually steer our while loop. Yeah. So first, as we see in example, so the actual yeah, we can actually do do this. So the opcode will be our where the instruction pointer points, and the literal value will be where our instruction pointer +1. And we also have something that's called a combo. We will actually just add a local function for this. So we have a kind of get combo. Combo. So by doing that, we can. So the combo will also be at the instruction pointer +1, but you will use either or actually. So that's okay. So then we have to have a switch on the opcode. Yeah. So let's define our different. Just gonna do this very quickly. So that we save time here. Yeah, so it will be like 1, 2, 3, 4, 5, 6. Yeah, 6 and 7. We had 7 opcodes. So the first that we are going to look at will be called ADV. So let's go back to the text here. So these instructions work as this. So the ADV instruction is called, which is opcode 0, performs division. So the numerator is the value of the A register. The denominator is found by raising 2 to the power of the instruction's combo operand. So an operand of 2 would divide A by 4 to XOR 2. An operand of 5 would divide A by 2 XOR B. So the result of division operand is truncated to an integer and then written to the A register. Yeah, so it's pretty straightforward actually. So we will when we find an opcode of 0, which is the ADV, we will set the A, as we set the A to A divided by the combo to the power of 2. So the next will be BXL. That will kind of yeah. So the BXL instruction, which is opcode 1, calculate bitwise XOR of register B and the instruction's literal operand, and then stores the result in register B. So we get a link here to an XOR. Let's say that a bitwise XOR is a binary operation, takes 2 bit patterns. Yeah. You can read, if you want, you can read about this. Well, we basically switch the bytes. So this bitwise XOR of register B and the instruction's literal operand then stores the result in register B. That will actually be this. So B will be XOR equals literal values. So we can write it like this, and this symbol here is actually short for XOR. So the next will be BST and BST. The BST instruction, which is opcode 2, calculates the value of its combo operand modulo 8, thereby keeping its lowest 3 bits, then writes that value to the B register. So it will be a little bit similar. So the B, but instead of using the literal, we will use the combo. So we will just do a simple modulo 8 by the. Okay, so let's go to the next. The next is the JNZ instruction of code 3. This instruction doesn't do anything if the register A is 0. However, if the register is not 0, it jumps by setting the instruction pointer to the value of its literal operand. If this instruction jumps, the instruction pointer is not increased by 2 after this instruction. Yeah, it's a little bit. This text actually is a little bit. Like this is set by it jumps by setting the instruction pointer to the value of its literal operand. If this instruction jumps, the instruction pointer is not increased by 2 after this instruction. So this thing is a little bit cryptic, I think. It would be easier just to say what it actually is doing is that for the JNZ opcode, we will actually just do this. So we will set the instruction pointer to, well, if A is 0, we will just we keep it unchanged, and if it's not 0, then we will set it to the literal value -1. That's what's kind of why they said that in the text. And the next is the BXC. So you can notice that this part 1 of this problem is pretty straightforward actually. You just have to actually read the instructions, and you have to read them pretty carefully, otherwise you might miss something. So the BXC instruction opcode 4 calculates the bitwise XOR of register B and register C, then stores the result in register B. It says for legacy reasons this instruction reads an operand but ignore. Yeah, well, it just says that basically that depends on how you code it, but yeah, if you have this kind of as a generic set, you would probably do it like that, but it will be more. This is actually actually some variation of the BXL. So BXC is actually just taking the B XOR C, B XOR equals C, and our opcode 5 will be out. And just to read it, so the out instruction is opcode 5 calculates the value of its combo operand modulo 8 and outputs that value. If the operand outputs multiple values, they are separated by commas. As we are just going to add it to our list. We don't have to care about that. So basically what we say is output add which will be combo modulate. So the next code 6 will be our BDV, and let's read about BDV. So the BDV instruction works exactly like the ADV instruction, except that the result is stored in the B register. The numerator is still read from the A register. So yeah, this will be more or less a copy of the ADV instruction. We will just do it. We will just set the value to the B register instead of the A register, as it said. And we can actually just read about it, because the next will be actually the same. So the CDV is the same, but it sets the C register instead. So we have this. Yeah. So, and of course we will increase our instruction pointer by 2 each iteration. Yeah, I think we're pretty done here. So we can like do, and to get our part 1 answer, let's just go back to the so this will be our expected output from our program. So let's just go ahead and run it. Switch here. So we start the program here. So 46356352210, and that should be our part 1 answer for our test input. Yeah. So let's dig in here, because as I said before, this is a pretty easy part 1, and the only thing you have to be careful is that you read these instructions very carefully, and by doing that you don't actually have to, and probably it's probably good if you know things about how to do bitwise operations, but in any sense, doing part 1 is pretty straightforward, and you will probably not most people, I think, could do it. Basically, part 2, on the other hand, is a whole nother thing. So, digging deeper in the device manual, you discover the problem. This program is supposed to output another copy of the program. Unfortunately, the value in register A seems to have been corrupted. So you need to find a new value to which you can initialize register A so that the program's output instructions produce an exact copy of the program itself. So what I want here, and I kind of define a new example here. And what you want, well, what this program states is that the program input, they want to know how to get that input, what to set the A register to get that as an output. So for this example, 117440 will, if we set the A register to that, we will get this as the output. So this is actually a problem that if you look at me at my real answer here, you would see that it's practically impossible to run this as a brute force solution. On a normal computer, this would probably take, yeah, I'm not even sure how long this will take. It will probably be an infinite thing, more or less. But and I did actually see someone who actually did this puzzle using some hardware assisted thing, and actually did it in a couple of seconds, brute force. But it will take that. So of course, when I did this problem, I just kind of just did a while loop, checking for the that the output should be equal to the output obviously my puzzle output, and just kept calling this run program method, sending in a value starting from 0, and just kept it going. And I saw when I had it running for like 3, 4 or up to 10 minutes or something, I would see that, well, this would never work. I have to find another thing. I kept it running in the background, kept thinking about a new solution, and basically what you need to do is to understand something is about a program. So I did kind of a reverse engineering thing of it, and I found that A could be divided by 8. So that may be thinking. So to do this, to come up with the solution I did, I think it's better to actually show the code itself, and then we can talk about it a little bit. So just for simplicity's sake, I will just add that to our code here. So we have kind of a, yeah, so this is basically so this is basically our part 2 code. So it's pretty small, pretty good. You can see that this is a recursive program, and the yeah. So when I did a real when I solved this puzzle, I started with ints, and then I kind of quickly realized I had longs, so I just did a replace int with longs all through the program. That's why, but the program lists will not need to be longs. It's just the registers that need to be longs. Yeah. So the this will kind of do. It will use a type of DFS operation to find the correct result. So we will have to. We can just do it like this. It will not need to be an int long. Yeah. So this is the actual. This is what we are looking for, and we will actually also replace our example values here. We can just comment out our part 1 thing. So looking at this, we will see that we now have new values. Well, it's not really important to get. We only want this because the A value here is not important, and we're not going to use it. So this will be our. This is what we are looking for. So we initialize that as a target, but we want to check this in reverse. So basically, what we do, we just call it the reverse method. This will reverse that list. So instead of 035, it will be 043530 instead. From that way. So let's just think about this. So this takes in that list of that program list. It will take in the target, which will be this list in reverse. We will start off by setting A to 0, and we have also a depth variable here. So the depth will kind of will tell us how far in our search pattern we have reached, and at the maximum we will take the number of items in the target, which will be the same as in the program, of course. So when we have reached that depth, we will just return what the A was at that time. And we have a for loop here, so that's where we actually found that this 8 thing, because that's what I found when I reversed engineered the code. I found this kind of thing. So the 8. So we will only go from 0 to 8 and we will also take our A, multiply it by 8, and adding the I here. So that will kind of steer our initial A value that we send into our run program method. So we will get its output. So basically we start by actually sending in 0 here or something, that we will get some type of output. And we always need to check if it has any values at all. But then we are interested in that the first item, or the index 0 of the output, should be equal to the depth, and the depth will be 0 of the target at first try. So if this is true, then we have found. If we find the kind of, and this will be kind of our starting pattern. So if we find that value, if those values are correct, then we could go into our DFS routine, and that will kind of just do recursive jump, add the next chunk of A's, increases depth, and we will be back here again, and then we will kind of check the next thing we will check is then we will check the next part of our list, and we will go and take this in chunks this way until we are, and the result will be kind of, in the end we will return it either there or there. So that's basically how I found. I know that this is a bit cryptic. And it's a little bit hard to explain all the things about this, but this is what I found, and and it runs really fast. So if we run this, we get our expected answer. Yeah. So this was this day, and I know there are mixed feelings about this kind of problems. Some people like it, some people don't, and I know. I mean, we haven't had this kind of computer simulation in any puzzles since I think it was. Well, I haven't done the entire 2021. Well, almost. I think it wasn't after 2019 there were, because in 2019 they had a lot of puzzles related to that in-code computer, and people was complaining about that because people who do this for the competition, they don't want that. So let's see, maybe we get to revisit this computer in some of the future problems. But as far as for this problem, I think part 2 was pretty funny to do, or pretty fun to do. It's a real challenge actually, but part 1 it was more or less straightforward. Okay, bye bye and see you on the next one.